Good afternoon to all. Welcome to Transfer Phenomena in Bioprocess Engineering Week 5 NPTEL course. So, the first class week 5 we will discuss about the fundamental of flow through the porous media. So, what we are going to learn from this here, what is porous media and explain the importance in the transfer phenomena, because the transfer phenomena the porous media is a very important. Then another one is for the structural properties of the porous media, including porosity, tortuosity, then specific surface area, relate them to the fluid transport behavior. The next one is for what is the differentiate between there is a superficial velocity is there, superficial velocity, then interstitial velocity, and calculate these velocities for the flow through packed bed. So, analyze how the porous media characteristics influence the hydrodynamics, then permeability, pressure drop, mass transfer, and overall reactor performance. So, today lecture we will discuss about the porous media, that is a very important. Then another one is for how the structural properties of porous media, including porosity, that point. The last one is for what is exactly differentiate between superficial velocity and then interstitial velocity. So far we studied the previous classes the fluid flow through the pipe and channel. So, example started with the Reynolds number, laminar flow, turbulent flow, then Huygens-Poiseuille equation for laminar flow, drag coefficient, like that we discussed so many the pipes and this one. But where the geometry is well defined and then fluid flow through a single continuous passage. But however, here we are going to discuss about the lot of biological activities there, many biological and then chemical engineering system are totally fundamentally different compared to other points. So, instead of single flow channel, the fluid must travel through the complex network, that is a complex network here of the interconnected microscopic pores. So, this type of flow always we called as known as a flow through the porous media, for definition. Then what is a porous medium? The porous medium contains a numerous interconnected void space. The void space numerous interconnected. It's like interconnected that allow the fluid movement while the surrounding the solid matrix provide the mechanical support. Unlike pipe flow, normal pipe flow, the flow path is straight. Normal pipe flow here, the flow path is straight and then well defined, but the pathway in the porous media are highly irregular because and continuously changes in the direction. If you take ordinary pipe flow, the direction is always straight line, but when you talk about the porous media through this one, the flow but highly irregular because there is lot of particles and void space are there and it continuously changes the direction of that one. So, what is a common example of in bioprocess engineering, or the first one for nutrient solution flowing through the packed bed bioreactor. There is a packed bed bioreactor, but nutrient the flow, that is the first one. The second one, the mobile phase flowing through the chromatographic column, another example, the best example. The third one is the oxygen diffusion through the microbial biofilm. So, there is a diffusion, dispersion, so many things are there. The diffusion is the concentration difference, the driving force here. The last one, water transport through the soil during bioremediation. So, we will discuss lot of problem bioremediation. The bioremediation, how the water transport through the soil, that is another for the best example for the porous media, this one. So, because of this complex geometry, the pores and the conventional equation, lot of equations are already there, such as the Huygens-Poiseuille equation cannot be applied directly, because we cannot apply the laminar flow equation, Huygens-Poiseuille equation directly here. So, of course, we have to modify the equation. This leads to the Darcy law help the describe the flow of fluids in the porous medium. So, what is porous medium here? The porous medium, the definition here, the porous medium is a solid material. This is porous medium, the solid material containing and the interconnected network of void space, or we call as the pores, through which the fluids flow here. So, all type of fluid through pores always pass here. So, the porous structures consist as a solid matrix, then pore spaces, then interconnected channels. So, the porous structure, whatever the porous structure, it's a totally like three types is here. One is the solid matrix, then the pore spaces, then interconnected channels. So, these pores provide the pathway for movement and transport. Movement and transport, that the driving force is the velocity gradient. Driving force the velocity gradient. Then the mass transport, the driving force the concentration. Wherever concentration, then definitely it through the pore transfer taking place. The last one is for heat transport. The heat transport is the driving force the temperature. So, these pores provide the pathway for all three type of transfer. One is the momentum, another is a mass transport, then heat transport. So, the pore may contain liquid, gas and the mixture of the fluids. So, the fluid transport occurs only through these interconnected void. There is a void space is there and pore is there, but all type of the fluid transfer through the interconnected voids here. The solid phase remains stationary, it is not moving, the solid phase always say stationary, but only the fluid moves through the pore network. There is a continuous pore network, through that only the fluids are moving here. Unlike a pipe where every fluid particle follow the relatively straight path, there is a straight path, everyone follow that one, but the fluid in the porous media continuously changes in a direction because of irregular arrangement of force. If you take normal the fluid particle, it goes straight path, but whenever if you use the porous media, but definitely direction all will be changed because of irregular arrangement of pores. Therefore, the transport of porous media is considerably more complicated than ordinary pipe flow. If you take normal pipe flow, the flow through is very easy, but whenever if you use the porous media, it is a very complicated and it is one of the toughest process. So, why the flow through porous media is very important? In bioprocess engineering, the porous media plays an important role because some biological reaction often occur on or within the porous materials. So, most of the biological reaction it occurs on porous material or within the porous materials. So, the best example for the packed bed bioreactors. So, the packed bed bioreactor, how the packed bed, this is a packed bed, there is a particle is not moving, the particles are stationary, that is called packed bed. Packed bed, whatever the particles are loaded, it is a stationary. So, but only the pores, via pores only all type of whatever you are passing the liquid, gas always pass through the pores. So, the immobilized enzymes or microorganism are attached to the porous particle. There is a porous particle there, the immobilized enzyme, the microorganism attached to this one. But then the nutrient solution, because we need nutrient solution that flow through the packed bed. For survival of microorganism, we have to pass some nutrient solution that also flows through the packed bed, through packed bed only. So, the reactant diffuse into the spores. So, whatever the reactant, there is a pore, it gets diffuse the pore. If once a diffusion, then automatically biochemical reaction also occurs inside the pores. So, there is a pore and then immobilized enzyme through the nutrient solution flow through the packed bed, first point. Then the reactant diffusion enter the pore. Then there is a biochemical reaction occurs inside the pores. Then once the reaction occurred, then finally we get the product that again diffuse back into the flowing liquid. So, once the product form, then again started to come outside the flowing liquid in the normal this one. So, there is a reaction. Once the reaction over, then product comes. Once the product's done, then automatically it come out, then it flow through the normal the packed bed. So, thus the reactor performance depends simultaneously on the fluid flow like diffusion, that is the main this one, then biochemical reaction. So, finally all reaction everything occur, then we will get a product in the packed bed reactor. So, example 2, what is this one? Chromatography. Chromatography, where normally used the protein purification is carried out inside the porous resin particle. The mobile phase transports biomolecule through the column. So, normally there is a mobile phase inside, it transport biomolecule through the column. Then the molecule start what happened, diffuse into the pore. There is a pore where the selective adsorption occurs. The whatever the molecule, it get diffused to the pore, there is a selective adsorption occurs. So, once then the efficiency of the separation, finally we want a separation, the efficient separation strongly depend on the flow of characteristics inside the porous bed. The inside the porous bed, how the separation this one, that is the main function of that one. The third point, the third example, filtration. What is filtration? During microfiltration, there is a micro, macro, nanofiltration is there, or during microfiltration or sterile filtration, the liquid passes through the porous membrane. The pores, what will happen? Allow the water, whatever the pore already is there, it allows the water or nutrient to pass while retaining the microorganism or suspended particles. So, the pore size mainly determine the separation efficiency. So, now what is the classification of porous media? So, there is a three, one is the based on origin, natural porous media is there, then engineered porous media is there. So, natural porous media, these occurs normally naturally in the environment, but the examples here, the soil is the best for porous media, then sand, then rocks. So, different type of examples are there. Then engineered porous media here, these are the manufactured for specific engineering application. The first one is for naturally we are getting that one, but another one is for we are manufactured for specific engineering application. Sometimes you want to use to remove of certain pollutants. So, then we need the specific engineering manufacture, we prepare that one. So, example it include a packed catalyzed beds, then there is a chromatography resins, then membrane filters. The activated carbon we use so many places for removal of heavy metal, antibiotics, then ions, all type of things. Activated carbon is the one of the best for removal of that one. Then the ceramic filters, at last the polymer foams. So, basically two type of here, one is the natural porous media that occurs automatically, it is always there naturally, the soil, sand and all. For engineers porous media, we have to prepare based on the application. So, these are best examples, starts with the activated carbon, then ceramic filters, all this one. Even the ceramic filters, we have ceramic membrane filtration. Sometimes if you want to use the petroleum based water, there also we will use for the ceramic membrane this one. So, based on the uniformity, there is a two type of porous media here. One is a homogeneous, the other one is a heterogeneous. Of course, homogeneous we always know that one. The pore structure is the uniform throughout the material. There is a homogeneous throughout the material, it's a uniform. So, normally in the packed bed, the glass beads will use, it's a uniform packed bed glass beads, because the pore structure is the throughout the column is a uniform. Heterogeneous, the pore size, porosity varies spatially. So, definitely heterogeneous, the porosity we will discuss that one. Then the pore size also it vary the spatially, wherever this direction it always vary. So, example natural soils, then soil contain different type of pore size and different type of porosity, all type of this one. Then we call that this one is a heterogeneous. Homogeneous is the uniform the pore structure throughout the material. So, the microstructure porous media, especially the internal structure, determine how the fluid moves. Then important structural features include pore size, that is a very important. If the pore size determine the amount of fluid that can occupy the medium, because the pore size will determine the how much amount of the fluid can occupy the whatever medium we are using here. So, normally the larger pores generally decrease the hydraulic resistance. So, whenever the pore size are very high, larger pores, it is a decrease the hydraulic resistance. Then pore connectivity, the first one is for pore size, the second one is for pore connectivity. Pore connectivity indicates whether the pores are interconnected. So many pores are there, whether all pores are highly interconnected or not. So, if you disconnected pores definitely contribute the little to the fluid flow. It should be a highly connected, interconnected. So, then it will give more this one. Then third one is the pore shape. What is the pore shape? How that one? Normal the pore shape may be circular or elongated, irregular, slit shaped that one. The shape influences the flow resistance. Whatever the shape, it influences the flow resistance. The last one is for surface roughness. It's control the wall friction and also affect the adsorption. So, these are the microstructure of porous media, especially starts with the pore size, then pore connectivity, then pore shape, that is also important, play a role here, and finally the surface roughness. So, what is porosity? The porosity normally we called as a epsilon. The epsilon is the media defined a ratio of the most fundamental structure parameters, the ratio of volume of the pores divided by the total bulk volume of media. So, we call the epsilon the volume occupied by force. The first one is volume of void, then what is the total volume of the porous material. So, porosity is a dimensionless and it is also one number. The value starts with the 0 and end with the 1. It is always 0 to 1 the porosity value. The porosity, if what do you mean 0.40, because it is always falls 0 to 1. If it is 0.40, then the total material 40% material consists of void space, because that is a void volume by total volume. If 40% of this one, that is the void space, other 60% consists the solid material. So, whenever higher porosity, it generally results in the larger void volume. Of course, it is a lower resistance and higher permeability, reduced pressure drop. The pressure drop get reduced because the pressure drop is reduced. However, the excessive high porosity, the porosity value very high, it may reduce the mechanical strength. The porosity very high, then the mechanical strength automatically get decrease. So, another is a tortuosity. its a porosity alone cannot completely describe the nature of flow. So, that the second important is the tortuosity. Here it measure how the winding actual flow path is compared to with the straight distance. So, mathematically we write tau equal to LE by L. L is the effective flow path, then L stands the straight distance. If tau equal to 1, then automatically LE equal to L. So, then the flow path is perfectly straight. The flow path is perfectly straight. If tau equal to greater than 1, then the fluid must travel a longer distance because of the curved force. So, this is all discussion here. Then what will happen if higher tortuosity leads to longer residence time, then lower permeability, of course the diffusion gets slow, then larger pressure loss will be a very high. So, what is the example here? Inside microbial biofilm, oxygen molecules must move through the highly EPS channels. Consequently, the oxygen penetration become limited. It is always creating the anaerobic zone. So, then next is the specific surface area. The specific surface area represent the internal surface available the fluid solid interaction. The specific surface area AV in the AS internal surface area by volume. So, that we call as a specific surface area. There is a meter square per kg, the total volume. So, here internal surface area, then V is the total volume. The large specific area, it gives a enhanced absorption, then catalytic reactions, enzyme immobilization, then microbial attachments. So, what is the best example for this one? The porous silica particle. Normally the porous silica particle for used for the enzyme immobilization, it possesses enormous surface area allowing high enzyme loading and improve the reactor productivity. So, that is if you increase the surface area, then automatically most of the all type of process will get a efficiency also get increased. So, what are the relationship between structural parameters here? We discussed the transfer fluid depend all three parameters simultaneously. One is the porosity. Porosity is the void volume by total volume. It leads the reduced pressure drop which increase the permeability. Same way for increasing tortuosity leads to increase the hydraulic resistance which eventually decrease the permeability. Increasing specific surface area definitely it improve the catalytic activity, but may increase the whenever if we increase the surface area, it may increase the frictional resistance also simultaneously get increase. So, definitely the designing porous media requires we have to balance all these effects. So, now velocity in through porous media, unlike flow in the empty pipe, normal pipe, the presence of solid particle reduce the space available for the fluid. So, whenever the particle, there is no particle, is a empty flow, there is no particle inside, you are just passing through this one. So, there exist the two different velocities, one is the superficial velocity, then another one is the interstitial velocity. So, basically these velocities are fundamental in analyzing hydrodynamics, mass transfer, then pressure drop, residence time, then fluidization and then reactor performance. So, what is superficial velocity? Superficial velocity define the volumetric flow rate, it is a meter cube per second volumetric flow rate, then there is a total cross sectional area of the reactor meter square. So, then we will get meter per second. So, the superficial velocity US we write US, U superficial velocity. So, Q is the volumetric flow rate, then the area, the total cross sectional area meter square. Although this is not a true fluid velocity inside the bed, but it is extremely useful when you serve as the standard engineering parameter for comparing different reactor system. The superficial velocity very important, because we are calculating with the inside there is no particle inside, it is empty, we are calculating the velocity. So, then interstitial velocity, its average velocity of fluid flow through a void space between the particles. Since only the fraction of bed is available, then Ui, we called Ui equal to Us, Us the superficial velocity divided by the porosity. Then Ui we can write that Us we can write Q by A, already epsilon is there, we can write Ui equal to this one. So, this will give for the actual average velocity experienced by the fluid. So, there is an interstitial velocity, unlike superficial velocity, the interstitial velocity considers particle packing, then bed porosity, then what are the available flow area. So, example, if we suppose 40% the reactor is void, then what is the meaning of that one? That is the meaning here, the 40% cross section area carry the fluid, whatever the fluids here. The same fluid must therefore pass through the much smaller area, consequently the fluid velocity increases. So, if interstitial velocity is higher, these are the one. So, there is a mathematical relationship, area of void equal to epsilon to area. Of course, this we know, Ui equal to interstitial velocity U equal to Q by A void, then Ui we can write this is Us slip velocity, then ratio of slip velocity by porosity, we can write this one Ui. So, since epsilon is less than 1, then it follows the Ui greater than Us, interstitial velocity greater than the Us. So, then the interstitial velocity is always greater than the superficial velocity in the packed bed. So, problem 1 we will discuss, it is a very simple problem. The reactor has an internal diameter, that is internal diameter 0.15 meter. The substrate solution is pumped through the reactor, the flow rate is 2 liter per minute. The flow rate is 2 liter per minute, the flow rate. The packed bed has a porosity epsilon value 0.40. So, what they are asking, determine the cross sectional area of the reactor, then the superficial velocity Us, then interstitial velocity Ui, then the percentage increase of the interstitial velocity over the superficial velocity. So, totally 4 they ask here. First one by one calculate. The problem already given, diameter, reactor diameter is there 0.15 meter. You try to use through the problem SI units. Then the volumetric flow rate is here, that is a 2 liter per minute volumetric flow rate. Then there is a bed porosity epsilon is a 0.40. Of course, now we know the Q equal to 2 liter per minute, you convert in terms of meter cube per second. Then after conversion, we will get a Q value is in terms of meter cube per second. So, that is a volumetric flow rate. So, once the volumetric flow rate done, then we need cross sectional area, that is a cross area pi d square by 4. So, the diameter is already the problem itself given, the diameter of reactors 0.15. So, 0.15 is there, then we get from here the area of the reactor, that is a calculate the reactor cross sectional area. Area we got this one. So, we know area and we know Q also we know, area also we know, then we can get the velocity. What velocity here? The superficial velocity, that is a Us equal to Q by A. So, Q already we got answer, then area also already we calculated, substitute and get the value of the superficial velocity. So, what is the interpretation here? This assume the reactor completely empty and ignore the presence of catalyst particles. And it is therefore and the apparent viscosity it is used for reactor sizing, then hydraulic calculation also. So, then interstitial velocity, so that is ui equal to Vs by epsilon, the superficial velocity we calculate already, then epsilon we know, then we calculate the ui value is always greater than the us. So, that u is a interstitial velocity. Although through the superficial velocity appears to be very small, superficial velocity appears very small, but the liquid actually the moves much faster than the void space, because 40% reactor volume is only available in the flow. So, next, what is the percentage of increase in velocity? So, there is a ratio of ui interstitial velocity, then us superficial velocity. Once you calculate, the percentage gets increases 150%. Or alternatively, what is the ratio of this one? Then that in the interstitial velocity is a 2.5 times of superficial velocity, this one. Say example, if it is 2.5 times of the superficial velocity us equal to ui. So, what are the key takeaways here? Is a porous medium consists solid matrix is containing interconnected pores through the which the fluids flow. The geometry of the pore network strongly influences the momentum, heat, then mass transport. So, what is porosity? We discussed its quantify the fraction of void space available for the fluid flow. So, then tortuosity accounts its increased path length, it is caused by the winding nature of the pores. Then the specific surface area, it gives definitely solid fluid solid interaction and gives surface area. It is definitely useful for adsorption, then catalysis. So, whenever if you use a immobilized bioprocess. So, these structural properties directly influence the permeability, then and pressure drop, and is forming the base of Darcy law, which will be discussed in forthcoming lectures. Thank you.